Hi guys, welcome back. We are going to cover chapter 4 today already. Hope you guys are doing good. Hope these lectures are helping you in every way possible, right? So chapter 4 is a little bit longer. There's a lot of stuff to cover today. We're going to be looking at the first element of weather and climate. So if you remember chapter 3, we ended with those different elements of weather and climate. I think it was temperature, pressure, moisture content, and wind, right? Humidity and wind. So today we're going to be looking at insolation and temperature, that first element of weather and climate. So what happens with the radiation from the sun and when it hits the earth? Like how is that distributed? Where does it go? Different processes that heat the atmosphere closer to the surface of the earth, so the troposphere, and how that influences weather and climate, okay? So this is one of the most fundamental of all the Earth systems, the warming of Earth's atmosphere and its surface by the sun. All right, so we're going to look at how that happens, looking at that energy transfer from the sun to the Earth. So let's get started. When we talk about energy, I keep using this word. Remember, in this chapter, it'll be energy from the sun, right? But when we talk about energy, heat, and temperature, let's kind of look at these words and differentiate them. So you can pause it here and write down all these definitions. These are great to have. Energy. What is energy? Energy is what makes things move, right? For example, it takes energy to cause something to move faster or to change direction or to break something down or to break apart. There's different forms of energy, right? There's kinetic energy, chemical energy, radiant energy, gravitational potential. And remember that energy can never be created nor destroyed. So that's the first law of thermodynamics. We don't have to get into that. We're not going to get into that. I'm a geography teacher, a geography professor, I'm not a physics professor, chemistry. So I don't have the knowledge that another professor would have on that. But the first law of thermodynamics means that energy is not created nor destroyed. We have the same amount of energy that we've had since, I guess, the beginning, right? So when energy hits, or when the sun hits the surface of the earth or the atmosphere above it, it's kind of downgraded into a lesser form, or it's released in heat, but nothing just disappears. It's reused in a way, right? And so we'll get to how that happens. So energy is really what makes things move, okay? And now temperature, what's the difference? So when you have temperature, okay, when you have energy, you can say that, let's see, if you put a pot of water to boil, it takes energy to move those molecules of water, right? They start moving around and jiggling around and bumping into each other, okay? You can't see it happen. Maybe towards the end you can, but anytime something is heated or has heat, or yeah, like when you put a pot of water to boil, those molecules start to bump into each other and they're moving faster and faster, okay? So now once those molecules are jiggling more, that means that this object, or whatever it is we're talking about, has greater kinetic energy. It's moving more, so the temperature is higher. That's why hotter things have higher temperatures, because that energy is making those molecules jiggle together or move around more. The temperature is a description of the energy, of kinetic energy. Okay, so temperature and heat are not the same thing. Temperature is the description of the kinetic energy. Now, heat is completely different. Heat is energy transferred from one object to another. For example, really easy, when you're at the gym, and I miss the gym, working out, right? You got your 15-pound dumbbells or 10, whatever, right? You're working out, it's arm day, you put them down. Then you get your phone and you snap a picture, take a selfie, post it on Snapchat. Then you pick up those dumbbells again, and what do you feel? usually you feel that those dumbbells still have the heat that you transferred onto them, right? Hopefully you guys understand this. Or like sometimes when you're saying hello to a person, you shake their hand, which is kind of like, it sounds weird now because we don't even like hug people anymore, right? But when you shake a person's hand, sometimes you could feel their heat, right? And that heat transfers onto you. Or even a better example, if you're making, I don't know, macaroni and cheese, and you're stirring the pot and you leave that metal spoon or ladle in there, then you grab it. What do you feel? Hopefully you don't burn yourself, but you feel that heat that has transferred from the mac and cheese or from the boiling water or whatever, right, to another object. Okay, so that is heat. Those are the differences between these three words. Okay, heat refers to the energy that is transferred from one object to another with a higher temperature to another, okay? Heat is energy transferred from one object with a higher temperature to another object with a lower temperature, okay? Sometimes the term thermal energy is used interchangeably with the term heat, but just make a note of these three words, and if I were to ask you like on the quiz or on the exam, energy and heat are basically the same thing. Is that true or false? That is false, right? All right, good. So that is energy and heat. How do we measure temperature? So we use different instruments to measure temperature. We have a Fahrenheit scale, a Celsius scale, a Kelvin scale. What I want you to know about this slide is that the most widely used in the United States, the scale most widely used is Fahrenheit. And so Celsius is used in most other countries, which is weird. I think our metric system in the United States makes us look like idiots when we travel abroad, right? I don't know if anyone's experienced that. Almost everywhere else uses the same metric system, and when we get like, even when I go to Mexico often, it's like Celsius, and you're like, okay, what does 30 degrees Celsius actually mean? And then you feel really dumb because, I mean, everybody else knows, right? So Fahrenheit scale is the most widely scale used in the United States, whereas Celsius is used in most other countries. And the Kelvin scale is used for scientific purposes because it measures what we call absolute temperatures, okay? Fahrenheit scale used most widely in the United States, write that down. Celsius scale used in most other countries. It is the accepted component of the international system of measurement. And the Kelvin scale is used for scientific purposes, and it is measured what is called absolute temperatures, meaning that the scale begins at absolute zero. Okay, that's all you need to know about that. It's just kind of like this introduction to heat and energy, okay? And again, if it is very basic because this is a physical geography class, but it's just what you need to know for the rest of today. So now let's look at really the type of energy we're going to be looking at today for this chapter. It is solar energy. It's energy from the sun. The sun is the source of energy for Earth's atmosphere, and you're going to see in the future and in future lectures that that is really what powers the entire atmospheric circulation, okay? You're going to see that the uneven warming of Earth's surface is what gives us our wind, what moves our weather systems, our clouds, brings in rain, moves away rain, gives us these ridges of high pressure, those different movements of pressure systems and what we're experiencing here. So it's not like, you know, it's hot because the sun is beaming on this spot of the earth. That is not really what's happening. So hopefully by the end of the semester, you're going to really understand when the weather lady or the weather guy says, oh, there's a ridge of high pressure. So we're going to have really, really clear, sunny, hot days, what that actually means, okay? So the sun is a source of Earth's energy for the Earth's atmosphere. Energy is also released from inside the Earth from radioactive decay of elements like uranium, thorium, potassium. So we do get a small percent of energy from inside the Earth, but when we're looking at energy that drives the atmospheric processes, and that's what we're concerned with today, it's energy from the sun. okay? The sun supplies almost all of the energy that drives atmospheric processes. In this unequal warming of the earth by the sun is ultimately what puts our atmosphere in motion. How cool, right? Energy from the sun. So when we look at the sun, obviously, when you're closer to the sun, the rays are more intense, and as you move further away from the sun, the rays are less intense. Now, a lot of these photos and images that I use for my lectures come straight from the book and the resources that are given to us as teachers, as instructors. Some of them are really weird, and you'll see that today. They're just like really straightforward, or like, okay, duh, like why do you have to show this? But you'll see in this lecture that a lot of them are really like awkward. But this picture shows the closer you are to whatever object is emitting that heat, the shorter the wavelengths, right? So from crest to crest, here it's shorter, versus over here, crest to crest, here it's longer. So closer to hot objects, the wavelengths are shorter, right? Further away, the wavelengths are longer, okay? So I want you to kind of get that from this slide. All right, so let's look at electromagnetic radiation. So the sun gives off energy in the form of electromagnetic radiation, also known as radiant energy. These, in science, I kind of want to take that fear away from a lot of students that are afraid of science or math. A lot of times in science, there's terms that are just, I say sciencey, right? It just means something that you already know. And in academia, you just got to learn that there's a lot of terms that might mean the same thing, right? Like if we were to go to a hike and I want to like sound smart and fancy, and we were hiking by, I don't know, by a river, I would say, oh, look at this beautiful riparian ecosystem surrounded by flora and fauna, right? Now that's like really pretentious of me to do that. I wouldn't do that, right? But if I want to impress someone, like if you want to impress somebody on a date, you would say that. All you're really saying is we're hiking next to a river and there's a lot of plants and animals. So in science, there's a lot of these like very, not loaded terms, but like flowery terms, right? And it just makes you sound smart. Well, you are smart. But what I'm trying to say is don't be afraid of all these fancy terms. Just learn what they mean, and it'll be easier to grasp things. So radiant energy is energy from the sun, emitted as electromagnetic radiation, right? Waves travel out from the sun at lines at the speed of light. Only a small percent of sun's energy is intercepted by Earth. So I have a lamp here, right? Say this is the sun. We're tilted away from the sun right now. Nope, we're tilted towards the sun right now, right? We're in summer. Doesn't matter. So all the energy from the sun, yeah, it's intercepted by Earth, but there's so much more potential energy, and we only capture a small amount of it. So solar energy is a great type of clean energy, right? Renewable energy. Like we don't even use a small percentage of what we can use. And the discovery of using solar energy was done years and years ago. I want to say in the 50s, we discovered that we can use and harvest energy from the sun to power things. Think about that. Think about how much more advanced or how much cleaner our world would be if we said, oh, you know what, let's not use coal, let's start using energy from the sun. How amazing that would be. But again, greed is more powerful, and coal was pretty cheap. So, you know, I don't want to say that we should have used energy from the sun, or, you know, humans are horrible. But you know what I'm saying? Like if we would have used energy from the sun when it was discovered that we can use it for clean energy, think of how much cleaner our earth would be. Maybe there would be less wars too, right? Over oil. Who knows? I mean, the possibilities are endless, right? The sun gives off energy in the form of electromagnetic radiation, also known as radiant energy. We experience different kinds of electromagnetic radiation, such as visible light, microwaves, X-rays, and radio waves. Electromagnetic radiation entails the flow of energy in form of waves. The waves travel outward from the sun at the speed of light. The waves travel through space without loss of energy, but because they are coming from a spherical body, the sun, their intensity continuously diminishes. The Earth receives an enormous amount of energy from the sun. Solar energy is viewed as an important source of renewable energy to generate electricity. So, talking about renewable energy, we do get a lot of energy from the sun, and it's a great source of renewable energy. So, a little bit about solar farms. Now we are seeing this used more than even just 10 years ago, right? Solar energy. So the Mojave Desert, if you've ever seen On the Way to Vegas, I think, right, is where you see one of the world's, well, the United States' largest solar farms. It powers over 232,000 homes, maybe even more, but it does have this little consequence. It does create something called a lake effect. And from far away, it looks like a lake, like a mirage, you know, and it attracts birds because they think that there's going to be insects there. So they are attracted to kind of like this lake-like effect. And once they fly into this zone, they are killed instantly because you have, what happens is, right? You have this central receiver, right? And these heliostats surrounding this solar receiver. So it's like a mirror. The sun reflects and beams straight into this receiver where you have water that is then heated up because of that sunlight. And then it turns into steam, and that steam powers a turbine, and that produces electricity that is sent to the grid. That's like an easy peasy explanation, right? Really easy. But that's kind of how it works, okay? And so this is what it looks like. And as those birds fly in, they burn up and die. Literally, they fall and smoke is coming off of them, and the workers that work there, they call them streamers because of the smoke that they produce as they're falling to their death. How sad, right? But also, birds are not the smartest animals in the bunch. If you remember being a kid and a bird got stuck in the cafeteria, do you remember how often that happened? And like, do you remember it was like, oh my God, there was a bird in the cafeteria today? Yeah, it was like the biggest thing in the world, right? Except crows. Crows are actually very intelligent animals and kind of scary. They have facial recognition. They can remember a human face if you've done something to them. Even like a year ago, they remember your face. So if you guys are interested in that, there is a documentary called A Murder of Crows or something like that. I watched it. It's kind of scary. So respect the crows that you see. They're very smart. They, what they do is some of them will take like a seed or whatever it is that they're going to eat, and they wait around. They'll drop it on purpose and wait around because they know cars will go over it and open that seed. Isn't that crazy? They're super smart. So they also have facial recognition, which is amazing. That's not often. All right, the electromagnetic spectrum. Electromagnetic radiation can be classified on wavelength. Remember I showed you that picture? Closer to the object emitting heat, the shorter the wavelength. Furthest away from the object emitting heat, the longer the wavelength, right? So we classify it on wavelength in the electromagnetic spectrum. Geographers are most concerned with visible light, UV radiation, and infrared radiation. The distance between the crest of one wave to the next is like the length, the wavelength, okay? So here is the electromagnetic radiation spectrum, sorry. And shorter wavelengths, obviously, they're much more powerful. Something from cosmic rays, gamma rays, X-rays, UV radiation, all the way to long radio waves, AM radio waves, right? Those are not so harmful. So what we're concerned with, obviously, is this area here as geographers, because we do use infrared radiation for mapping objects, and forgot the name. I was in a class where we used a lot of infrared radiation to map Oh, well, who cares? You are more concerned with that area as a geographer. Okay, that's all you need to know for this slide. All right, so let's look at what happens with that energy from the sun once it goes through and hits the surface of the earth, okay? So a couple things. Insolation. This is the total incoming solar radiation received at the top of the atmosphere. So remember, we have all these different layers of the atmosphere, right? We have the surface of Earth, troposphere, stratosphere, mesosphere, thermosphere, exosphere, right? You guys remember that? And a good way, I should have taught you guys this last week, to remember that is, I always do this. You can think of something that you will remember: TSMTE, troposphere, stratosphere, mesosphere, thermosphere, exosphere. The sick man took echinacea. And echinacea is actually really good for your immune system. I don't know. Think of something to remember that. Anyways. Okay, so energy from the sun. Incoming solar energy received at the top of the atmosphere. Some of it is going to travel through the atmosphere and hit the surface of Earth, but right away some of it is just reflected out into space, okay? So not all of that energy just goes and heats the surface of the Earth and the atmosphere. Some of it is just reflected back out into space. The rest passes through the atmosphere, okay? It is believed to be constant when averaged over a year. Some of the insolation is reflected off the atmosphere back into space. The remaining may pass through the atmosphere. It can be transformed either before or after reaching Earth's surface. So we're going to look at some basic warming and cooling processes in the atmosphere. Okay, these are physical. Remember, we're looking at how energy from the sun, radiant energy, comes in through the atmosphere and how it's moved around, the physical processes that involve the movement of this energy. Some of it is just re-radiated out into space, but what happens to the rest of it? Okay, so we're going to look at these actually fancy, sciencey words that involve the process of the transfer of energy, okay? This is the process of the transfer of energy when we're looking at insolation or energy from the sun and the atmosphere. Okay, so there's a lot of words here that we're going to get through. It's a lot, right? But I have a slide for each of these, and on each slide you have the definition and I'll explain. So don't worry about writing all these down because there is a slide for each of them, and then you're going to be able to write down that term and definition or explanation for it, okay? So let's start with the first one. Radiation. This is the process by which electromagnetic radiation is emitted, also known as emission. So all objects emit electromagnetic energy, but hotter objects are more intense radiators. All it's saying is the sun radiates electromagnetic energy. Okay, that's it. Now, the opposite of that would be what? If it's not emitting, it would be absorbing, right? So electromagnetic waves strike an object, and that heat or that energy may be assimilated or absorbed. Okay, so yeah, it's just you're absorbing something. Okay, or assimilating something. Electromagnetic waves strike an object, and that object may assimilate that energy. Different materials have different absorptive capabilities. All right, so radiation absorption. Now, next slide. Reflection. If the energy is not absorbed by an object, it is reflected, okay? It is reflected. So a term that's really important for physical geography, very related to reflection, but here we go again with these fancy words, is albedo, okay? So think of like a really hot day, right? What color do you know that you're not supposed to wear in the sun? Black, right? Why? Because it absorbs more heat. That's why, right? What about what color should you wear? White, because it reflects heat. Think about if you've ever been snowboarding or skiing. I'm not privileged enough to make those trips, but I know that people who do go snowboarding, they have to really put a lot of sunblock on, and after they wear their little goggles. I know nothing about this sport. What I do know is that because the snow is so white, all that sunlight is reflected into their face, so they get really sunburned. So that's an example of albedo. So when we look at, now albedo is a reflectivity capability of an object. So anything that is the color black is going to absorb more, so it's going to reflect less. So it's less albedo. Anything that is white will reflect more, so it has high albedo, right? Overall reflectivity of an object or surface, and it's given a percentage. So when we look at the surface of Earth, now this is a horrible picture because this is like a political map, or globe. If you were to think of the Earth and the colors that are found on the planet, what's found on the planet? Green, gray, right? If you were to say blue, it's actually, if you look far away, it's a very dark blue. So water actually absorbs, the ocean absorbs heat because overall it's a darker surface. And our ice caps, they reflect a lot of sunlight. So already when you have energy from the sun coming in, our ice caps help a lot of that energy move away. So unfortunately, we're losing a lot of our natural ice, our ice caps in our poles. So as time goes on, once those shrink, the sunlight that comes in, instead of it being reflected, well, there's less of that to reflect in those ice caps, and there's going to be more ocean. So it's absorbing more heat, which is going to turn up the heat and then melt even more of those ice caps. So we call this a positive feedback effect. One change incurs another change. It's kind of like this runaway effect, a snowball effect, if you will. Things are just going to get worse. I know it sounds really bleak, but we're already in a warming trend, right? We're already losing our glaciers. So already we're losing this reflection that naturally the Earth has. Those ice caps, the more of them we have, the more sunlight they reflect. Are you guys following this? So once they start to disappear, there's going to be more water exposed, meaning more heat absorption. So that's going to in turn cause more warming. So if you think that climate change is happening pretty quickly, there's a lot of things like that, these positive feedback loops that are just getting started. And unfortunately, it's like this snowball effect that we're not going to be able to stop once it happens. So albedo. And now let me show you a picture, a really cool picture from the book. Right? Like what? But actually, I kind of put this up here for comedic relief because what does this even, like, I think my explanation was better. But obviously, if you're wearing a dark colored suit, you're going to absorb more heat versus this white colored suit, you're going to reflect more heat. I don't really like this picture. All right, so albedo, are we clear on that? That's a really important term for this, actually the entire course, albedo, okay? And here are some albedo values. Obviously, fresh snow is going to have the highest albedo percentage. Make sure you have that down in your notes. Anything dark is going to have low albedo percentage, like black asphalt, concrete. Forests and grasslands, they have a pretty higher than average albedo reflection. Bodies of water, whatever, 10 to 60%. So it really depends on the type of body of water and where it's at, okay? Okay, moving on. So we did radiation, absorption, reflection, we did albedo. Now we're still looking at how energy comes in through the atmosphere and what happens to it, right? So now scattering. So gas and particulate matter, which you guys know is also called aerosols, right? Can deflect light waves and redirect them. So these are scattered around the atmosphere. They're just buoyant, tiny, they're hanging out there. They're known as particulates or aerosols, correct? Once the sunlight comes in, it beams off of them, or they scatter that sunlight instead of that sunlight coming through, okay? That's called scattering. They redirect those light waves, all right? Transmission, when sunlight comes in, it passes through a medium. That's it. Like if something is clear, like water, the atmosphere, a window, a clear medium, it's the transmission of energy through a medium. And here is one of those great pictures. Yeah, so here you have this really cool car, which is kind of like a mixture of a Celine, like a Ford GT Mustang, right? It has double exhaust in the back. This is from the book, guys. So you have the sunlight coming in, and it passes through the medium, which would be the windows, right? And then if you don't have tinted windows, you know, on a hot day, I mean, it sucks to be inside that car, especially if you have leather seats. I don't have leather seats, but I hear that you get hemorrhoids if you sit on hot seats. I don't know how true that is. So all that sunlight comes in and it's trapped inside. This is also like this little greenhouse effect in here. And we'll talk about that in a little bit. So actually, that's the next slide. One of the most important of all the basic cooling and warming processes is the greenhouse effect. So this is actually a good picture to kind of explain the greenhouse effect. So you have sunlight that comes in, passes through a medium, it starts to warm like the leather seats and everything in there, and it can't come back out of those windows. So what happens when you open that door and it's like mid-August, it's super hot in there, right? Because all that energy has been trapped in there. It's like it's a little oven. So that would be the greenhouse effect. Out of all these processes, remember albedo and the greenhouse effect. These are probably some of the most important. Okay, you have incoming solar radiation, heats the surface of the earth, heats the sand, heats the water, heats the grass, right? And it wants to move back out into outer space, but remember, we have all these little variable gases or greenhouse gases trapped in the atmosphere. So that sunlight that wants to go back out into outer space, it gets trapped. And what happens? It gets warmer and warmer and warmer. So we call this global warming or climate change or the greenhouse effect, okay? Same thing if you're like in the winter and you're watching a movie and you have your little blanket on. That's like a mini greenhouse effect because your heat wants to escape, but the blanket traps it, so it's nice and warm, okay? So incoming shortwave radiation heats the surface. Long wave radiation cannot be re-radiated out because it's trapped because of greenhouse gases, which we learned are also variable gases in the atmosphere. Water vapor, CO2, methane, nitrous oxide, ozone, also known as variable gases. Those little molecules, they trap all that sunlight. Are they natural? Yes. Is the greenhouse effect good? Yes, it is, because if we didn't have the greenhouse effect, it would be so hot. I mean, it would be so cold on the planet. We need it to keep us warm. However, there are too many of these greenhouse gases in the atmosphere. Now, a lot of man-made ones, anthropogenic caused ones. So it is exacerbating, I don't even know if I'm saying that word right. It is making the greenhouse effect stronger because there's so many of those greenhouse gases in the atmosphere. Okay? So this is a really important slide, a really important topic here, the greenhouse effect, okay? All right, moving down that list, we did radiation, absorption, reflection, scattering, transmission, the greenhouse effect. Next is conduction. I know you guys have learned this before. This is the transfer of heat from one molecule to another without changing in the relative positions. I gave you guys a great example of this earlier. Like if you're making spaghetti sauce, right, and you have a metal ladle and you leave it and you post it on Instagram and you're like, hey everybody, I know how to cook, and you take a picture, then you go back and get that metal spoon, what happens? You're probably going to burn yourself, right? Hopefully not. But metal is a great conductor of heat. So it transfers heat from one molecule to another, right? Conduction, through conduction. Heat is transferred through conduction. Next one, convection. Energy is transferred from one point to another by predominantly vertical circulation of a fluid like air or water, okay? So if you're in an older home, like this apartment here, I have actually, my heater is at the bottom right there. When I lived where I grew up with my parents, the vents are at the top. So I noticed that here, when it's wintertime, and our home is a little apart, not that little, but it's a smaller house than my parents' house. It warms up much quicker. Why? Because hot air rises. So as hot air rises, it gets heavier, then sinks, and then it does like the circular motion, okay? It's a circular motion of air. So the entire space heats more efficiently and more quickly, versus if you have the vents at the top, it like stays up there, the hot air, and then eventually it falls. So that takes a little bit longer to heat a space or heat a home. So that's a great example, this image here. I like this picture from the book, so I can't say I hate all of them. And advection, this is the transfer of warm or cool air horizontally, okay? Let me see, where am I at? When dominant direction of energy transfer is moving in a horizontal movement, it is called advection. In the atmosphere, wind may transfer warm or cool air horizontally from one place to another through advection. And then we have latent heat, which is a phase change involving an exchange of energy. So the physical state of water in the atmosphere frequently changes. So it goes from water vapor to water droplet, back to water vapor. It can go to a solid, to ice. So the state of water is always changing in the atmosphere, ice to liquid, water to vapor, so on. Any phase change involving an exchange of energy is known as latent heat, okay? Because it takes energy. It even takes energy for water to turn into ice. And that's hard to understand, but if you were to leave like a thermometer in the little cup of water that you're turning into ice, right before that moment, before it freezes, it actually goes up in temperature, just slightly. But that's because it's taking energy for water to turn into a solid. And it's really interesting. I saw a really cool video on it, how the temperature actually gets a little bit warmer before it turns to freezing. It's pretty cool. And adiabatic cooling and adiabatic warming. I do not have definitions for this, but I do want you to pay attention to this picture here. So adiabatic cooling and adiabatic warming. When you have warm air is buoyant and it rises, okay? As warm air rises, once it gets to a certain level in the troposphere or in altitude, we know that as you go up, it gets colder, okay? And as that warm air rises, it expands and cools. Cold air is heavier, it's denser, it's going to sink. So adiabatic cooling is warm air that rises, and as it rises, it expands and gets colder. We call that adiabatic cooling. On the other side of that, you have a parcel of air that is cold, it's heavier, and as it descends, you have heavier, it's under a lot of pressure, but it compresses. And as those molecules bump into each other, it gets warm. So air that descends gets warmer. We call that adiabatic warming. Okay? So you can rewind this and play it again. That's the nice thing about teaching virtually. I don't have to repeat it, but as air rises, it expands and it gets cooler. We call that adiabatic cooling. As cold air falls, it compresses and gets warmer. We call that adiabatic warming. All right, cool. We went through that really quickly. Now we're moving into the last portion of chapter 4, okay? Okay, so the last part of chapter 4, Earth's solar radiation budget. This is just what happens with the energy from the sun when it comes in. You can think of it like a budget. Is it balanced over time? Yes, because energy is not created nor destroyed. So all the energy from the sun that comes in eventually makes its way back out, right? That's all this is. Overall, there's a long-term energy balance. Earth's energy budget, there's an annual balance between incoming and outgoing radiation. The annual balance between incoming and outgoing radiation is called the global energy budget. The illustration that I will show you uses 100 to represent the units of energy or insolation coming from the sun, and at the very end, over time, and it's not like instantly, but over time it is balanced. If you'll notice here, it uses 100 just to keep things simple. So say there's 100 units of energy coming in, solar radiation. About 31 of those units is reflected from the top of the atmosphere and the surface of Earth, and scattered radiation is just lost into space through Earth's albedo and the top of the atmosphere. And then you have 45% or 45 units absorbed from Earth's surface, and then over time that's just re-radiated out into space. But look, it comes in at 100 and leaves at 100. Why? Because energy cannot be created nor destroyed. It doesn't disappear. It's just either degraded or turned into a different form of energy, or it's just re-radiated out back into space. Okay, that's it. This is pretty easy to grasp. This is just Earth's solar radiation budget. So you have radiation loss from reflection, absorption, direct absorption, and surface to atmosphere energy transfer. So how is the atmosphere heated or warmed? Some of it is heated through, I think I'm going to get to this next, okay, in the next slides. All right, so when we talk about land and water temperature contrast, we know that Earth is mostly water, okay? I should get a better globe for my classes. So Earth is mostly water. 70% of the surface of Earth is water. And then you have land. 30% of it is land for now, right? And then if all our ice melts, who knows, right? So when we talk about land versus water, what heats up more rapidly? Do you think land heats up more rapidly or water heats up more rapidly? And this is where I wish we were in a classroom and you would answer, right? And I would say, oh, you guys are actually all wrong. Or I would say, oh, wow, you guys are actually all correct, right? So the answer is land heats and cools more rapidly than water. Now, why is that? So these are the 4 different reasons why water takes longer to heat up than land. Number 1, specific heat. Water has a higher specific heat than land. The specific heat of water is 5 times greater than land. So water must absorb 5 times the amount of energy to show the same temperature of land. So it takes more energy to heat water than it takes land. Okay, transmission, the sun's rays penetrate the water more deeply. Think about the ocean. The rays of the sun had to go through the top of the ocean or water body of water. Are you guys following this? And heat all of that versus land, rays from the sun just heat the land. Does that make sense? Right? So because of transmission, which is a word we learned today, the sun's rays penetrate water more deeply than they do land. Water is a better transmitter of radiation than land. And mobility, water is always mixing around and moving. So when that top layer moves around, it's not like that heat just stays there, right? It moves around, so it takes longer to heat up water than land that is not moving. It's just like, beam, the sun heats it. That's it, right? And the last one, evaporative cooling. Water is obviously moist, right? There's this unlimited availability of moisture in water. So the surface is always evaporating, right? Does that make sense? So it takes longer for water to heat and cool than land. Now, why is this important? What does this have to do with anything? Well, because we're going to be getting into weather and climate, it's important to know that bodies of water heat and cool less rapidly than land. I should have stated that differently. Why? Because, what does this all mean? Oh, see, here's one of those great pictures. It's just what I explained. What does this all mean? Continentality. So this has a lot to do on weather and the locations of Earth, right? So like places that are closer to an ocean, like San Diego or Los Angeles, their weather is going to be completely different than somewhere that is completely landlocked or inland, right? Like Kansas City, right? They don't have any access or proximity to an ocean versus Seattle, San Francisco. They're on the same latitude. They should get the same, on the same hemisphere in the same season, right? So you would think that they have the same incoming solar radiation, Kansas City and San Francisco, the same everything, same, you know, but San Francisco is close to an ocean and Kansas City is not. So that makes a huge difference. We call that continentality. Now let's look at this chart here. It explains just what I was saying. You have January, February, March, April, May, June. Jason Derulo. You can't unsee that now, right? Okay, this is the different months of the year. On this side, you have your temperature, right? And we don't even know what Celsius is because we're American. So San Diego and Dallas, they are on the same latitude, same kind of example, right? Kansas City and San Francisco. So same latitude, same hemisphere. You would think that they have the same temperature trends. So for August, Dallas is at, let's say, 90 degrees versus San Diego's probably 70, right? That's a huge difference, same month. What about those cold months? December, January, Dallas is like 41, 42 degrees. That's so freaking cold. And San Diego is like at 58. So that's a big difference, right? So your proximity to the ocean has a lot to do with what you're experiencing in terms of seasons or weather, okay? So keep that in mind. We call that continentality. So continentality means that the interior of continents have more severe weather than proximity to the ocean. Let me see, I think I have. Okay, here we go. This is what I want you guys to write down. Pause me and write this down. Interior of continents are where we find the hottest and coldest areas. That's what I was trying to say. The interior of continents is where we find the hottest and coldest areas. Okay? All right, so I think that's that. Oh, just a couple things. The IPCC is the Intergovernmental Panel on Climate Change. This is really the data, the leading body for the assessment of climate change. It assesses the most recent scientific information worldwide relevant to climate change, okay? I think that's it, you guys. Yeah, right now I think they're past the 6th assessment, but what they do is they get information from all over the world, global data, and they put it together, and different types of evidence that is proving that our climate is changing is our rising sea levels because our ice is melting, warming temperatures, increased wildfires. This is just some evidence, right? Changes in precipitation patterns, compromised coastlines. Even here in the United States, we are seeing that, we are living that real time. Louisiana and Miami is experiencing loss of coastlines. Miami is at or below sea level. I mean, they're at the point where, I'm looking at my globe, they're at the point where a large hurricane can like take out the Keys or Miami Beach. Literally, right now they are pumping out seawater, ocean water, because the water is just invading so much. All right, so I'm gonna have some links and some discussion on that. So I hope you guys are enjoying these videos. I really am. It gives me something to look forward to and do. Obviously, it's my job. I have to do it, but it just makes me feel like I have a little bit more worth, because it was hard. Like the last 6 months, it's been tough. You know, I was used to teaching 6 classes, 2 different campuses. At nighttime, teaching my fitness classes, I work at 3 different gyms, and that's out of the picture. So it has been hard, but this is giving me a little bit more motivation. I don't know why I just went on that rant. All right, you guys, let me know if you need anything else.